We now discuss the solution of a problem from the section number theory, and this question is based on the concepts of the number of prime factors. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the section C. The given question is, for a positive integer small n, let big omega n denote the number of prime factors of n counted with multiplicity. Number of prime factors of n counted with multiplicity. For instance, omega of 3 is equal to 1. Omega of 6 is equal to omega of 9 is equal to 2. Let p greater than 3 be a prime number, and let n is equal to p into p plus 2 into p plus 4. Which of the following statements are true? We are given four options. Option 1, omega of capital N greater than or equal to 3. Option 2, there exists primes p greater than 3 such that omega of capital N is equal to 3. Option 3, p can never be the smallest prime divisor of capital N. Option 4, p can be the smallest prime divisor of N. Prime divisor of capital N. We are given a definition for omega of small n, where small n is a positive integer. So for a positive integer n, omega n is defined as the number of prime factors of n counted with multiplicity. You are given with an example also. Omega of 3 is equal to 1. Why? Because 3 has only one prime factor, namely 3. Omega of 6 is equal to 2 because 6 has prime factors 2 and 3. So it has two prime factors, namely 2 and 3. Therefore, omega of 6 is equal to 2. Omega of 9 is 3 square. The 3 has multiplicity 2. Therefore, omega of 9 is 2. That is 3 repeated twice. Let p be a prime number greater than 3, and capital N is a number given by p into p plus 2 into p plus 4. Then we have to discuss the validity of the given following four statements. Which of the following statements are true? That is the question. We now discuss the solution of the problem in detail. For small n belongs to the set of natural numbers, we have omega of n stands for the number of prime factors of small n counted with multiplicity. We are given p is a prime number, p greater than 3, and capital N is a natural number given by p into p plus 2 into p plus 4. P is prime, p greater than 3 will imply either p is congruent to 1 mod 3 or p is congruent to 2 mod 3. Yes. P is congruent to 1 mod 3 will imply p is equal to 3k plus 1. P is congruent to 2 mod 3 will imply p is equal to 3k plus 2 for some natural number k. Agreed. If p is equal to 3k plus 1, then p plus 2 will be 3k plus 1 plus 2, that is 3k plus 3, that is 3 times k plus 1. And when p is equal to 3k plus 1, p plus 4 will be 3k plus 1 plus 4, 3k plus 5. So capital N is equal to p 3k plus 1, p plus 2, 3 into k plus 1, p plus 4, that is 3k plus 5, that is capital N. Let's call this as the equation 1. If p is equal to 3k plus 2, if p is equal to 3k plus 2, p plus 4 is 3k plus 2 plus 4, that is 3k plus 6, that is 3 times k plus 2. Then capital N is equal to p, that is 3k plus 2. And p plus 2 is 3k plus 2 plus 2, that is 3k plus 4. And p plus 4 is 3 times k plus 2, which we have already seen. And capital N will be 3k plus 2 into 3k plus 4 multiplied by 3 multiplied by k plus 2. That is the equation 2. So from 1 and 2, what we observe is, n is the multiple of more than 3 factors. More than 3 factors. So more than 3 factors. So that's what we have noticed. And let's get into the options 1 and 2. Option 1 says omega of n greater than or equal to 3. Option 2, there exists primes p greater than 3 such that omega of n is exactly equal to 3. Now, we observe that from 1 and 2, we see that n has more than 3 factors. Right. When n has more than 3 factors, certainly n will have more than 3 prime factors. Further factorization may lead, and we'll get you have to express in terms of the prime factors. Therefore, when it has more than 3 factors, then certainly capital N will have more than 3 prime factors. So therefore, omega of n will count the number of prime factors of n counted with multiplicity. Then omega of n is strictly greater than 3. Therefore, the option 1 is true. And for any prime p greater than 3 and omega of n is greater than 3, therefore there does not exist any primes p greater than 3 such that omega of n is equal to 3. It is greater than 3, it is equal to 3 for no prime. So further, omega of n is equal to 3 for no prime p greater than 3. Therefore, the option 2 is not true. Thus, the option 1 is true. From option 1 and 2, option 1 is true. We continue in the next slide. That's what we have done in the last slide. Agreed. Option 3, we take p can never be the smallest prime divisor of n. Option 4, p can be the smallest prime divisor of n. Read these two things carefully, and if one is true, the other is false. Agreed. Now, from 1 and 2, we see that 3 is a prime. Yes, 3 is a prime. And 3 divides n in both the cases. So, 3 is a prime number and 3 divides n. And p is equal to 3k plus 1 is certainly bigger than 3 because k belongs to the set of natural numbers. Also, p is equal to 3k plus 2 is greater than 3 for k belongs to n. So that means 3 is the, so far as this is concerned, 3 is the smallest prime that divides n. Whereas p is equal to 3 plus k plus 1 is not a smallest prime that divides n. And so also 3k plus 2. P is not the smallest prime divisor of n. In fact, 3 is the smallest prime divisor of n. So the statement given in 3 is true. So the option 3 is true. Definitely option 4 is not true. Because p can be means for some values of k, but for no value of k, he can be a prime divisor. Prime divisor, because 3 is the prime divisor that is there, and that is the smallest prime divisor of n. Agreed? Agreed. So, the answer to this question is option 1 and option 3. So, that is the detailed discussion of the solution of the problem on the number of prime factors from the section number theory. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.